afternoon session, which will deal with the random field Ising model. So there will be a number of people intervening. Silvio Franz, Marco Picco, and Emilio Trevisani. And it's Silvio who's going to start. So please, Silvio.
So good afternoon, everybody. I am Silvio Franz. I'm a physicist here at TTNS and a statistical physicist. And actually, I was very much interested to the paper of Lava and the others on the random field Ising model. So I proposed to Raul to have a discussion without expecting a responsible discussion about random field Ising model. Something I'm not really an expert. So perhaps the first thing I will do, I will tell you my the random field Ising model comes from. I am interested to the problem of the glass transition and the glass state. Can you hear me?
I can hear you.
We can, but it's sometimes there are interruptions. The moments are not too frequent.
So let's see if it works better like that. So as I was saying, I'm interested to the random field Ising model because the physics of glasses. So in glasses, what you have at the glass transition is freezing of fluctuations. So if you think to a structural glass, meaning a liquid which becomes a glass, the configuration of the glass has disordered configuration of the liquid, except that the fluctuation of density, for example, remain frozen in while they average very rapidly in general in the liquid. So the order parameter in such a situation is the overlap between configurations. So if you take two configurations at random of a liquid at different times, they are as different as they can because they correlate very rapidly. But if you consider a glass, okay, the configurations have a large overlap. Thermal fluctuations, the glass remains stuck with some fluctuations, say, of density. And if you measure the overlap between that fluctuation between two configurations, you will find that this will be larger than random. Okay, so what you want to do is a theory of glasses in which the overlap plays the role of the order parameter, and write a sort of lambda energy glasses of without free energy functional, if you consider the field of the overlap for glasses. How do you do that? Well, you fix a reference configuration that you take the typical configuration of your system, and then you consider a second system with an attraction with the first one. Okay, and okay, so you define a measure of similarity between configurations. So say X and Y are two configurations of your system. You can define a Q of X and Y that locally in point X of space tells you how similar they are, configuration X and configuration Y. And then you introduce an attraction, maybe space dependent, and you add this attraction of the Hamiltonian, and you consider the conditional probability of y given x in presence of the attraction. Now, of course, here you see that x acts in a way as a disorder, as plays the same role as quench disorder in a disordered system, because you have that the normalization factor of the measure for y given x depends on x. Okay, so starting from that, you can define, for example, a large deviation functional as the free energy of your system, the average free energy averaged over the distribution of x, or you can construct more complicated objects, and those are interesting indeed, where you look at fluctuations of this average large deviation function. Okay, I wrote in here v of q. I should have written v of epsilon, and v of q you can define if you want as the Legendre transform in the usual way. So in this way you construct a Landau theory for the glass transition, and it's a theory in the random field in the sense that x, the configuration x that considered is a disordered configuration and can act as a disorder in the system. In fact,
can I ask a question?
Yes.
But in this formulation, you are trying to not to think about the physical origin of this qx, because I'm a bit confused. It's a bit put in by hand, this qx of xy.
It's put in by hand.
Yeah, meaning that there is no clear physical mechanism why the configuration y tries to be close to configuration x. Why does it physically?
Well, okay. The idea is that you have, basically many minima in the energy. Okay, this is a glass. So it's a system which has a complex energy landscape with many minima. The system will like to be close those minima, but you have many. Okay. The configuration X will select one. I mean, I'm giving you an intuitive view of what I'm doing. No? Configuration X will select one of those minima, okay, which is as good as all the other minima, as the glass is concerned. And this attraction, okay, you push the system close to the minimum that you have selected. Okay.
I guess it would be helpful to see some form for this function qx, because otherwise it's rather abstract, but maybe you will write it later.
What do you want to see? Sorry?
Some example of this function qx, because otherwise it's pretty abstract.
Okay, so if you have a spin system, do you see the blackboard?
Yeah, actually.
Okay. If you have a spin system, for example, you have Ising spin SI.
Can you write a bit lower, because that part of the blackboard is not visible? Yeah.
Okay, so let me write on the. Ising spin system, and of course you can represent, for example, the liquid in the in a lattice glass representation, you can discretize and use Ising spins. What you can do, you can define the overlap between two configurations S and S prime as sum over n, because you have n spins Si S prime I. Okay, so you see, so this is just a scalar product between the spins configurations, and this is large if the spins configurations are similar, and it is 0 if they are uncorrelated. And of course, you can then define a local
The sound has disappeared.
over here.
Yeah, now it's back.
You can. I don't know what happened.
And there is some bad distortion.
You can define a function. No, let me try like that. Yeah, probably. You can define a function W of R, which is say 1 on a length which is a fraction of the particle diameters, and you define the overlap between the configuration X and Y as W of Xi minus Yi. In reality, I mean, you can allow, for example, for permutations of the particles in Y and in X and Y, and so you would sum over I and J. Okay, so this would be a measure of the overlap between configuration X and configuration Y. So you see, the idea is if the fluctuations, if you have that the configuration of the system are similar, Q is high and other they are low. Okay, this can also be written, if you want, in terms of density as rho in position X of space of the configuration X of the system, W X minus Y, rho in position Y of configuration Y. Okay, so this is the overlap. Now, okay, as I was saying, the basic object can I mean, the problem is not where I keep it. So the basic object that you can consider is the average free energy as a function of in presence of this fraction. And you see that here the partition function depends on the configuration X. And so you can use replicas.
I'm sorry, Silvia, I have another question. So what is so this parameter epsilon that you introduced? In the end, which is it a regulator? What is the physical value of epsilon?
No, the physical meaning of epsilon, like
not the meaning, the value.
It's like a conjugated to the order parameter.
Well, I understand.
Like the magnetic field in a magnetic system.
No, no.
Okay, so in the magnetic system, you have that the order parameter is the magnetization, and H is the parameter conjugated to the magnetization.
But what is the magnetic field in your system? There is no magnetic field. You introduced this by hand.
No, but I have an order parameter. Okay, I introduce, and I want to define a field theory for that order parameter, and I introduce a source for that order parameter. Okay.
No, in the end, are you going to take epsilon to 0, or is it going to stay at some finite value?
Okay. So, of course, the system as it is has epsilon equal to 0, and you can use epsilon, for example, to generate correlation functions.
Okay.
Now, as a matter of fact, okay, epsilon finite has an interest. Okay? In particular, as I will show you, I will show you, but I will tell you that in the plane epsilon temperature, there is a line of phase transition that terminates with a critical point, and that critical point, okay, one can show that it's in the universality class of the random field model. Okay. Okay. But let me just arrive to that. So you see, you need to average over your reference configuration X the logarithm of the partition function. So you can do it with replicas. You introduce n-1 replicas. Why -1? Because 1 is X itself. And at the end, you have a system with n replicas, where the replicas from 2 to n are coupled to the replica number 1, and you want to send the number of replicas to 1. So the problem of glasses in this language is a problem in which you have an invariant and permutation, which is Sn-1, okay, because the replicas from 2 to n are equivalent, and you want to send n. X, as I was saying, as a sort of disorder which is self-induced, because it is the system that generates the disorder. And now you want to play the usual business of the phase transition, study the fluctuations of the order parameter and the transitions of the order parameter. Analogously to systems in a random field, there are two sources of fluctuations. In the random field, you have thermal and sample to sample, and here as well. You have thermal fluctuations, and you have sample to sample, which correspond to different choices of your reference configuration. Now, okay, within field theory, what you can see is that you can compute the phase diagram of your system, which has this appearance. There is in the plane temperature coupling. Oh, notice here that the origin is not 0, the origin of temperature. So this is a finite temperature. You have a line of phase transition between a situation in which you have a so at high temperature you have a low value of the overlap and a high value of the overlap at low temperature, okay, separated by this line. Now this line is a line. It was correct before. You are right. It was correct before. Okay. You are right. So this is low temperature, high field. It was correct before. the first theory. Low. So of course, I mean, you know, physics that you would like to describe is at epsilon equal to 0, but this line is interesting, and indeed it is a characteristic prediction. The existence of this line, it is a characteristic prediction of the theory that you can develop, of this theory that you can develop with. Q is the overlap, the order parameter. Okay. So the existence of this line is one of the characteristic prediction of the theory of classes that you can do starting from replicas and from, for example, a high dimensional starting point. Okay. And indeed, people have been numerical simulations numerical simulations, and have been finding evidence existence of this transition line, and for the fact that this line of this transition terminates with a critical point. Okay. Okay. For the physics of glasses, it is also important the spinodal of the low overlap phase. In particular, the point at epsilon to 0 is a point where a dynamical appears in mean field. Then, I mean, it is an artifact of mean field, but on the other hand, as so it has the characteristics like of an avoided critical point that attracts the systems up to a certain point and before becoming
so question, what is spinodal? I'm not sure what it means.
Okay, so first order phase transition is a point where you look at the field level, the free energy. The free energy, it looks like that with two degenerate minima. Okay, so this is the point of phase transition in mean field. I mean, then of course in finite dimension the free energy becomes convex, and you have Maxwell's construction. Now the spinodal within mean field is the point where one of the minimum exactly disappears. Okay. So this is what spinodal refers to.
And another question: where do actual real glasses live in that phase diagram? And which point do they live, or part of the diagram?
Real glasses live at epsilon equal to 0. Okay. There is a lot of discussion if this point that within mean field is an ideal glass phase transition point really exists in real glasses, and I would say that the question is not settled. But this is not the question that I would like to discuss today.
Okay.
Okay. Now, I would rather, point the attention and just to the fact that this point, this mode coupling theory, it is called mode coupling theory, spinodal point in this language. One can know that corresponds to a critical point, a critical point of an unstable theory with disorder, which is in the universality class, the spinodal of random field Ising. So it's a cube random field. Okay. On the other hand, the critical point itself in this phase diagram is in the universality class of the random field Ising model. When I say it's in the universality class, what I mean is that you can analyze perturbation theory. In perturbation theory, what you find is that the dominant synchronicities coincide with the ones of random field Ising model, and at the end, you end up with, passing from replicas. You make some formal manipulations, you end up to a Parisi-Surlas effective field theory of the random field Ising model, at least goes to the critical dimension. Okay, so this was just I am interested in the random field Ising model, and so let's start the discussion about the random field Ising model properly. The random field Ising model is the Ising in which you have electromagnetic interaction between spin variables in presence of a random field with short range correlations. Now, this model can have a paramagnetic ferromagnetic transition, and this is what you would like to describe. Okay, the first thing that you can ask is when the transition is going to exist. There is a very argument for that tells you that a transition exists in dimension larger than 2. The argument is very simple. Basically, you look at the stability of the magnetized phase and you ask, okay, you say, suppose that I have a region where suppose that I am in the plus phase. I have a region, the magnetic field is on average negative. And I ask if the fluctuation in which I reverse the spin in this region is going to destabilize the system. Now you can look at the energy balance for such an excitation, and you have certainly the term which is due to the fact that the magnetic field is negative, which goes like, since you have a random magnetic field, it goes like the square root of the volume of the excitation, and then you have an interface cost. You have an interface cost for producing the excitation. And if you make the balance between the two terms, you realize that the interface prevents you the excitations, large excitations in dimension larger than 2, and so in particular in 3 dimensions you have a transition. So this is the first thing, and then of course to analyze the equal 2 case it is much harder. Okay, so this is the existence of the transition. Then you can ask, okay, so what are the relevant quantities? So as I say, again, there are 2 sources of fluctuations. So you can look at correlation functions which are sensitive to one or the other kind of fluctuations. So you have a correlation function, traditionally is called connected correlation function, that is basically normal fluctuation of the overlap, and you have the so-called disconnected correlation function. But you see, it tells you how much which is sensitive essentially to the fluctuation of this. So you compute the average term magnetization over thermal fluctuations. You correlate in 2-point of space, and you consider the connected correlation function with respect to the distribution of the result. So this is the disconnected correlation function. And in general, the fluctuations due to disorder are much stronger than fluctuations due to thermal fluctuations, and effectively this is a manifestation of fact that you are dominated at the critical point by a zero temperature fixed point. Okay, so perturbation theory. Okay, so here you can define two critical exponents, one associated to the connected and one associated to the disconnected correlation function. A perturbation theory tells that the two exponents are identical, and moreover, there is the property of dimensional reduction. So the correlation functions, the disconnected correlation functions, which are the most singular ones of the system, coincide with the correlation functions of a pure model in a dimension which is lower than the actual dimension of the system by 2. This is perturbation theory. This is perturbation theory. This is perturbation theory. The question is, this is close to 6 dimension. Yes. Yes, this is only valid. This is valid in perturbation theory. The critical dimension, the upper critical dimension of the theory is 6. Okay, so the perturbation theory is a perturbation in 6 minus epsilon, and this is the result of perturbation. Now, okay, the physics is dominated by a zero temperature fixed point. So Parisi and Suras have rationalized the dimensional reduction, say, okay, you are dominated basically by the 3 level theory. And at the 3rd level of the theory, you should look at the stochastic differential equation, okay, in which the derivative of your free energy function is just equal to the exponent. If you do that, okay, you can construct and if you want to, for example, to look at average of a magnetic field of some observable, you can define a field theory putting the equation of motion into a delta function, add a functional determinant that normalizes the delta function with the modulus and average. So if you want to average over the solution. Now, if the stochastic equation has only one solution, what you can do, you can drop the absolute value of the determinant in a minimum. The determinant is positive. You drop the absolute value, and you end up in a theory, and then you can represent the delta function in Fourier transform and the determinant with fermions, and you end up with a theory which has which is DRST symmetric. Moreover, if your disorder is short range, in such a way that when you average, the only thing that you have to average in disorder is the term that comes from the Fourier representation of the delta function, you have a supersymmetry. You have a supersymmetry because essentially, if you introduce a superfield, you can see that this term that comes from the average over the disorder can be represented as you introduce a superfield introducing two Gassman variables, and in terms of the superfield, these terms that comes from the average over disorder have this representation. The total action can be written then as an integral over space and Grassmannian variable of potential, which depends on the superfield, plus phi super Laplacian phi, which is supersymmetric. It tells you that, for example, correlation functions are invariant under rotations of the superspace, and so they have the same form. They are functions of x squared plus theta bar. And this is obviously an enormous symmetry, because I mean you see that you can then the function has this form, and if you re-express in terms of the physical field, this tells you immediately, gives you immediately a relation between the disconnected and connected correlation function that in particular implies that eta is equal to eta bar. So you see, this tells that this function, GC is the derivative with the derivative with respect to S squared of GC. And it also so this gives you eta bar. Sorry?
Can you repeat questions, please?
No.
Who's asking?
No.
The question was not heard because we cannot hear the question.
You have the disconnected. Sorry, what I should have written is an overbar, because this is an average over the magnetic field. Is an average over the random field.
Silvio, if you receive
you don't have disconnected. The disconnected, you only have the connected.
Silvio, if you receive questions from the audience in the lecture hall, you should repeat them, because we cannot hear them.
Yeah, you're right. Please remember me, because I will tend to forget. So the question was, in this formalism, you have only one copy, and therefore you don't have disconnected correlation function. No, for the disconnected correlation function, you need just one copy. If you want a disconnected function for two different fields, you need more copies. But if you want phi of x, phi of 0 with a bar, I mean, one copy is enough. Okay, and this is what I have here. Huh? I mean, if you, okay, I mean, unfortunately, in 3 minutes, I will, this is not my theory. I mean, I'm explaining standard things. Okay. I was just reviewing Paris. But this is you know something that immediately shows that these two exponents are the same. Also, most importantly, you have the property of dimensional reduction. Dimensional reduction that evidently has to fail at low enough dimension. Dimensional reduction. So here the upper critical dimension is 6. And that will tell, I mean, if dimensional reduction was true, this would tell that in 3 dimensions you don't have a finite. but you have. Okay? So it has to be wrong. Okay, so let me just briefly mention what can be identified as the origin of phase of the supersymmetric theory and of dimensional reduction. So suppose that you take the stochastic equation that defines the stochastic equation of minimization of the Hamiltonian field. Now, of course, if you have multiple, first of all, the modulus of the determinant is different from the determinant. Moreover, you should basically you should just consider the ground state of the system, and if you consider the ground state of the system, you can have discontinuous jumps. So suppose that you have minima, different minima, many minima. And suppose that you act with some additional external field in addition to this. Now, when you change the field, this can provoke the fact that that the levels that correspond to different minima cross. Okay, and when you have level crossing, you have you must jump from one minimum and to the other, and this can lead to avalanches in which the field configurations are macroscopically different from in the two different. Okay. Now, if you look at and if you look to the, for example, to the to one of the word identities of the BST symmetry, one of the identities of the BST symmetry is just the fact that the connected correlation function, so the response function for the system, the minima of the minimum in which you are, is just the inverse of the curvature of your minimum, and this supposes that you indeed you are following the minimum. So if you have avalanches, this cannot be true. And this is the origin, I mean, it has been identified as the origin of breaking of supersymmetry. Okay. I will not, Emilio will talk about replica approach, so I will not talk about that. But what I would, the very last thing that I would like to mention is that indeed, the contribution of the avalanches can be appreciated if one really looks at configurations at different values of the field and compares solutions of the stochastic differential equations at different values of the field, and one looks at this kind of generalized disconnected correlation function. So this is magnetization, so total magnetization with the field H, total magnetization where the field has been moved a little bit. And one can argue that the contribution of the avalanches gives you a term which is proportional to the absolute value of the difference of field. This is a cusp singularity. I mean, we have here the word expert, one of the word experts of this kind of singularities, how to derive them theoretically. So, but this is what I wanted. And then Tarjous and Tissier analyzed this kind of singularity and related the breaking of or presence of supersymmetry to the typical size of avalanches. Avalanche that they occupy a portion of space of size L. The size of you can define a fractal dimension of the avalanche as the size of the avalanche that goes as L to the df, and according to the value of df and how it compares essentially with the dimensional space, you can have either dimensional reduction or supersymmetry integration. And if you accept some values, a value df equal 4, that I think that Kai derived the avalanches in dimension 6 or close to dimension 6, you find from these criteria that there is room for supersymmetry just below dimension 6. Okay. Now, very last thing that I would like to mention is that with people with, in particular, in the group of Tarjous and Tissier, with non-perturbative renormalization group, have found that breaking of dimensional reduction occurs below a dimension 0.1, which is close to what Slava and the collaborators seem to find. And okay, so this is everything I wanted to say, and now I will leave the word to Marco, and also I would like later discuss if we know something about the difference between the non-perturbative normalization group approach and the approach of Johan. Okay.
Okay, thank you, Silvio.
Is there time for a very short question?
Of course, yes. Go ahead.
So this stochastic differential equation approach, I would like to know if it should be considered as correct, but we just have to consider all solutions, or is this approach also like a priori approximate and we shouldn't believe it apart, we should consider it as a sort of toy model and we shouldn't trust it fully?
It is correct. You should consider the state. Okay, but you should have a theory that includes the fact that when you consider response functions, okay, you have a contribution from these avalanche events that can lead you very far in space. Okay, I think it is correct. You are attracted by the temperature fixed point, which means basically that the fluctuations due to disorder are much stronger than thermal fluctuations. So this is physical. I mean, this is somebody has been put into question. Okay. Except that you know, I think that the difficulty is to make a theory of the stochastic differential equation that takes into account the fact that the response does not simply, you know, the response that you have when your system lies in a big parabola and you push and you pull it and the system moves in the parabola. No, I mean, you can also have the fact that boom, you jump to another, you know, another place in space.
I'm just asking because I haven't seen in the literature like first principle derivation of this stochastic differential equation.
I mean,
because it's derived already, like starting from perturbation theory. Let's look at all diagrams.
No, I agree. I mean, you know, I agree.
Yeah.
But then there is the physics. I mean, you know.
So you I understand. You think every approach, you think it's a good physical picture, but maybe there are some extra effects which are not completely captured.
And also, so I mean, as you see, as you will see from Marco's talk, okay. What you do in numerical simulations, you minimize the Hamiltonian. Okay. So minimizing the Hamiltonian means that you consider the solution of the stochastic differential equation. You look at the ground state.
Okay.
Okay, so maybe we should change to Marco then. So thank you again, Silvio.
Ça marche. Okay. This is Silvio. Okay. You hear me?
The sound is good.
Okay, good. But we don't have microphones. Okay, just from organization point of view, we are 3 speakers, so I will try to be very short because then we will have a break and then the next speaker will speak after the break. If I can get my transparency. What I'm going to present is just a certain number of numerical results which have been obtained over the last few years, mostly by me and my collaborators, which are supposed to be quoted here somewhere on the transparency. Yeah, I will remove. I'm writing it. Okay, that's it. Yes. So in very short, I could make my talk in very few seconds and just telling you that basically we have made large simulations of a random field Ising model in 3, 4, 5 dimensions, and we tried to check a certain number of things. In particular, we tried the problem of universality. There exists a 2 or 3 exponent scenario. I will mention you what it is, and the dimensional reduction. And basically, we were able to obtain that in 5 dimensions. We believe that our results show that there exists dimensional reduction. So this is a very short version. Now I'm going to longer version. This is the point. I would. Okay. Okay, so this is the model which was already shown before. How do you on? Sorry, just move on. Oh, yeah. Okay, so this is the model which was already shown before by Silvio. Just to mention that this model is not realized experimentally, but it's known that it's equivalent to some experimental relevant model responding to the diluted antiferromagnetic model in a field. And this is a model which exists in real experimental realization. So it is also of interest in finite dimension. This model is in which we have added to the spin, to the Ising traditional model, a coupling of the spins with some random field. Okay, and then there is a ferromagnetic paramagnetic transition, as was explained before by Silvio. And we have the fact that the relevant dimension is body larger than 2. And so if we're doing numerical simulation, what we are interested in is 3, 4, 5, and 6, presumably. Okay, with 6 being the upper dimension, critical dimension. This is the phase diagram. So before, Silvio didn't mention a lot, but one thing which is interesting in this model, in particular, if one do a numerical simulation, is that it's a model in which it is expected that the critical point is at 0 temperature. That is, this is the traditional Ising model in function of the temperature. Okay, and this is the axis corresponding to introducing the random field, or more or less the strand of a random field. And it is expected, it is known actually, that close to the random field Ising critical point, the pressure is irrelevant. This is indicated by this arrow, while the influence of the field, external field, random external field, is irrelevant. It will take you out. So basically, the physics that we have, if we're trying to determine the Ising model, would be the same if we're replacing the temperature by the strength of the random field. Okay. Oops, I moved a bit too fast. Okay, here we were. So here there is some repetition with what was shown before by Silvio. If we're taking the mean field Hamiltonian corresponding to this model, and we use some random field with some replicated system, and we perform the average of the result, then one obtained such a term. So this is similar to what was done by Göteborg some days ago in his lecture. He was talking about the Potts model, things like that, but basically this is the same type of a system. And then we see that there exists some square term which appears here due to the random field. And then this means that the propagator is going to contain a non-diagonal term which is going to couple the different replicas. We inverse this propagator, one observes that there exist 2 terms, okay? One term which is going to propagate like 1 over k squared, and one like 1 over k4. And this is the reason for which there exist 2 types of propagators that are connected and disconnected. These are the same that we already introduced before by Silvio. Okay. And then, of course, this is at the level of a mean field, and we move below the upper critical dimension. Then, in principle, one expects that each of its propagator is going to have an anomalous dimension. So this means that while for the standard Ising model, when you move below the upper critical dimension, one has 2 exponents to characterize the system, nu and eta, or the thermal and the magnetic anomalous quantities. For a random field, we would expect that there is 3 such quantity, nu, eta, and eta bar, each of the eta being associated to a propagator, one of the propagators. But as already mentioned also by Silvio, if one performs perturbative computation in order epsilon 6 minus d, then one can see that at each order, there is a relation between the random field Ising model in d dimension and the Ising model in d minus 2 dimension. Okay, so there's a result obtained first by these people, and then one expects that eta is going to be equal to eta bar. So this should be one manifestation of the fact that the dimensional reduction exists. Next, this dimensional reduction is also explained by even supersymmetry. It was also said before by Silvio, so I will move on. And it is well known that this phase, for instance, in 3 dimensions, there exists a random field Ising model critical point, okay, which is well known. And so below this critical point, the system is ordering, while in 1 dimension, it's well known there is no ordering phase. So clearly this phase, at least in 3 dimensions. I also mentioned here again that we expect then that eta is different from eta bar, so we have 3 independent critical exponents. There was also another theory put down by Schwarz and other collaborators, in which we should get such a relation for reasons that I don't want to explain because it would be a little bit too long. But then for the people who spend a lot of time into that, there was a long question and long debates to knowing if we have really 2 or 3 independent exponents. Okay, so it jumped, so I don't know. Yeah, it jumped. Oh, it jumped a lot, this thing. Okay, so now the dimensional reduction is a sharp reality. So there's many reasons which have been put forward for the possible breaking of dimensional reduction on supersymmetry. One would be the existence of some non-perturbative effects due to bond-staying replicatory. The breakdown of perturbation theory, which could be done to a large number of Minima, or the existence of large-scale excitation. So this is also something that Silva has talking about. And in principle, we expect different type of scenario. And one of the motivation was to try to see if we can move a little bit in understanding a little bit better. One possibility would be that there is no perturbative effects, and then that the supersymmetry is destroyed immediately at d equals 6, okay? Or for small epsilon or even for d equals 6. It could be also existence of violation of the supersymmetry, which may be exponentially small. In this case, of course, it would be very difficult to find anything. Or there is also the possibility of the existence of this large scale excitation mentioned just before at the end by Silvio, and then computation by Tarjus and collaborator made over the last 5 or 10 years suggest that the supersymmetry would be broken at the dimension 5.1, meaning if we are below 5.1, there is no supersymmetry, no dimensional reduction, but it should be restored at 5.1. So when we started this work of numerical simulation, more or less we were at this level. Later on, there was some other works by Ikami using Bootstat, and more recently by the 3 people who also found out that the dimension close to 5 is probably something which is interesting. This is probably where we can start thinking about finding a dimensional reduction. Okay. Fine. So this was just a long introduction. So in our recent numerical work, what we have done is perform large-scale simulation in 3, 4, and 5 dimensions with the goal of examining the universality. Maybe we don't care so much about that, but as we mentioned, check the puzzle of a number of independent exponents. And the thing which interests more us here is to try to see if yes or no there exists some dimensional reduction in I dimension. Okay. So now I'm going to spend a few minutes giving you some real details about the simulation, but again, I'm going to move very fast. One thing that we have computed is that we had computed we have measured observables associated to some cumulants. So there is 3 quantity that we have computed, one which corresponds to the Binder cumulant, and then the 2 correlation lengths associated to the 2 propagators. The reason I mention all of them is because they're going to be useful later on when I'm going to speak about supersymmetry. These quantities, the definition of this quantity are given here. And from them, we're going to consider 3-dimensionless quantity. The fact that they are dimensionless are going to be very useful because they are going to allow us to make very precise determination of the critical points on the critical exponents. Okay. Essentially, the idea comes from the fact that if you have a dimensionless quantity, then you can use this following development. So again, this is things that you have already seen in previous lectures by Professor Aroni and compositor, I believe. Namely, it allows you to express this dimensionless quantity as a function of a deviation from the critical point, and also including the leading irrelevant operators, corrections. And this is something very important because it turns out that there is a lot of correction in the system. Then we solve numerically for 2 systems of 2 different sizes. We're checking the crossing of this quantity. We're making a small development which allows us to obtain omega plus 1 over nu. We plug it again in the previous quantity. We plug the solution in that one, and then we have a direct access to the omega. The determination of omega is something which is very important, okay? Because if you don't have a very definition of omega, you cannot measure anything. Just to show you directly what this corresponds to, it corresponds typically of making big simulations for two sizes, 6 and 12, and looking for a crossing. So this crossing is going to give one value, okay, of the value of the critical point for a given size, and then we want to go to the infinite limit, extrapolate that to the infinite limit. One important point to notice is that this is non-monotonic. The fact that it's non-monotonic can be observed by the fact that it increases and then it's going to re-decrease. Okay, and this is important, and this is the reason I mentioned here that we have checked different type of distribution, and we have also checked different type of quantities. I mentioned that we compute the Binder cumulant on 2 different types of correlation length, and the reason will become a little bit clear. The reason why will become clear a little bit later. So the fact that we have a non-monotonic behavior is of some importance, because in the past people were considering the random field Ising model were claiming that it's not even universal, meaning if you're taking a different type of distribution of the random fields, you're getting a different results. And of course, this is very bad. Okay, it's very bad for many reasons. And here I'm going to explain very quickly why these people were claiming that. So in all the measurements, people.
I'm sorry, Marco, I didn't understand. What was exactly non-monotonic? I got confused. Could you explain a bit again this point?
Computing a quantity, let's say the Binder cumulant, for different distribution of random fields, either the Gaussian random field or the Poissonian random field. And you're obtaining a different result. This was the claim.
But no, that is non-universal. But what is non-monotonic?
Oh. What is non-monotonic is the value of the crossing. This is, if you look here, it's 170, 178, and then it decreases again, 179. It's difficult to see, but this is here, and then it moves back in the other direction. But this is also non-monotonic. This is the value of U4 as you're increasing the size. This is for the 1 over L. U4 is the Binder cumulant. It's just the ratio of the 4th power of magnetization divided by the square of the square. Okay, and here what you're observing is that it goes down and then it goes up. Okay, and before in the old measurements, people were measuring typically up to 32. Now, if you're trying to extrapolate that one, you're extrapolating that one, and you're saying, okay, that's fine, but the extrapolation of that one more or less is going to be here. Okay, everyone agrees with that. The extrapolation of that one, if you're stopping here, is going to end up here. So basically, you're claiming that you're getting 2 different results. So the only way of seeing that you have universality is to go much bigger sizes. Okay, then if you separating this one is going to end up somewhere here, and if separating that one is going to end up here. So looking at this plot with this part, more or less everyone will agree that this is going to go to the same result. While if you're stopping here, it's not going to be here. But of course, in order to do that, you need to have much bigger sizes. And you also need to incorporate the fact that it's not monotonic, meaning that you have not only one correction, but more than one. Okay? So the only way of treating properly the random field Ising model in 3, 4, and 5 dimensions is by including many corrections. Okay. And with that, we were able to show that all the questions of universality are not even relevant. Basically, we claim that we can prove that we have universality, or at least it's compatible with the fact that we have universality. Okay. The next thing is, after we have argued that we have universality, we're going to use the fact that we had performed simulation for the Gaussian and the Poissonian distribution, and also 3 different quantities, because then it gives us access to many different measurements. And this is going to be useful when we're going to move in large dimension, and in particular, mentioned. Indeed, I'm going to show you. I don't know if I'm going to try to finish very quickly because I always run very late. I'm going to show you just 2 or 3 results, and then I'm going to move to a supersymmetry. So typically, these are the type of result that we obtain in 4 dimensions for the connected correlation length. These are the measurements which have been done for the 2 types of distribution of disorder that we considered, the Gaussian of the Poissonian disorder. And then this is for the crossing obtained from the connected correlation length, the disconnected correlation length on the same here. Okay. So the fact that we have many different quantities that we consider on 2 types of distribution of random field means that we can impose a joint fit. Okay, meaning we impose that there is a final point which is the same for all of them, and this helps us getting the different exponents which we want to measure. Okay, if we add only one measure, the error bar that we would have obtained here would have been 5 times bigger, 5 times bigger. Okay, so the fact that we have many types of quantity that we measure and we have different types of distribution of the random field, after we accept the fact that we have universality, which we are supposed to see, then allow us to get rather precise measurements. So these are the results that we obtain. I'm going to show later on the result for the random field Ising model. Just once, I am impression I'm missing some of my slides because it jumps. Okay, so this is equivalent in 5 dimensions, sorry. Of course, in 5 dimensions, the maximum size that we were able to simulate is smaller. I think there was one slide which I missed in which I was giving details on the simulation, but I think it's too late now. I'm going to move back. So in 3D, we were able to simulate system of the size 192 cube. In 4 dimensions, I think it was 60 at the power 4. And in 5 dimensions, it was 28 at the power 5, which is pretty big in terms of the total volume in the number of spins that you have on the number of simulations. But at the end, 28 is still not very, very big. So the consequence of all that is if I give you only the points of one of a quantity, it would be very difficult to extrapolate. But here we were able to put together many different quantities with the 2 types of distribution, and with that we were able to obtain some results that we believe to be accurate. So here I mentioned some of the results, but these results are going to be summarized in the next table. So these are the main results that we obtain here for the 3 case, 4 case, 5 case, etc. So quickly, this line just corresponds to the question of having 2 or 3 exponents. If we had 2 exponents, then the 2 exponents condition would imply that this is equal to 0. In the case of 3D, it's not very clear if it's true or not. It seems to be not true, but the error bars are rather big. In 4 dimensions, it's pretty clear that the 2 scenario doesn't work. We have 3 different exponents. In 5D, we don't really care very much about the scenario. Next, we want to check the dimensional reduction. Of course, it doesn't matter for the 3D case because we cannot go to one-dimensional Ising model. If you're taking the exponents corresponding to the 4D, and you compare with the one of the 2D Ising model, clearly the results are not the same. They're completely different, so there's no dimensional reduction in 4 dimensions. This is clear. Okay. Next, if you're looking from the 5D case and you're comparing with the 3-dimensional Ising model, you're seeing that there is a rather good agreement between the results. Nu is here, it's here. The agreement is maybe less good for eta on eta bar, but still, if you're taking into account the error bars, you're seeing that we are not very, very far from the result version, the result known from the Ising model. Same thing for beta, gamma, etc., and also omega, which is written here. Okay, so our conclusion is that with our numerical resolution, we claim that the results in 5D random field Ising model are compatible with the one of the 3D Ising model. Okay, sorry, just, yeah, okay. I'm going to move on for the last few minutes. I'm going to speak about the supersymmetry, because so far we have just shown that we have dimensional reduction. We want also to check if we have supersymmetry. In order to check if we have supersymmetry, what we need to do is to find some conditions. And one thing that I didn't mention in this table, I put here the values that we computed in our model, but I didn't compare with the ones in the 3D Ising model, essentially because it would have no sense. Indeed, this quantity usually undefined on some lattice with some periodic boundary condition, and taking the intercumulant on a 5-dimensional system with periodic boundary condition in 5D wouldn't make sense to compare with the same in 3D. In order to make the comparison, we need to do a little bit more job. And this is explained here. So basically what we have to do in order to test this prediction is to consider a special geometry in which we're taking a system which has 3 dimensions L fixed, and then the 2 other dimensions are going to be elongated, and we have to take the limit in which this is going to go to infinity. And the reason we want to do that is because when we start from a supersymmetric theory, if we expect that we have a supersymmetric theory in 5 dimensions or in D dimension, then we have some symmetry corresponding to all the on which gives rise to the supersymmetry. But when we're taking a finite system with fairly boundary conditions, we're breaking the rotational invariance. So we expect the supersymmetry is broken. So what we want to do is to restore part of the supersymmetry. And by taking these two directions, which are sent to infinity, we're restoring some O2 supersymmetry. And then it can be seen that this is enough to have the supersymmetry restored, and then having the dimensional reduction for these two dimensions. Okay. And numerically, what it means, essentially, it means that the quantities that I already defined before, the disconnected correlation function, can be defined in which we're only taking into account 3 of the dimension, and we forgot a little bit of the 2 other ones. And then we can compare this quantity with the same in 3 dimensions, imposing some normalization constant that we don't really know how to compute, but which is not position independent. And then the advantage is that this quantity can be used to compute. First, we compute the Fourier transform in a little bit complicated way, which is written here. And from this Fourier transform of the quantity, one can define a correlation length. So people who are not expert, the main point is that the correlation length is computed by taking the ratio of 2 of this Fourier transform propagator, and by taking the ratio, the Z, which was introduced, has disappeared. So we don't have to care about the normalization. And the same thing for the Binder cumulant, which is written again here. It's a power 4 on the power square at the square. So the Z, which was existing here, also disappeared. So these two quantities defined in such a way have the advantage to be able, we were able to compare them directly with the quantity in 3 dimensions and see if it works or not. If it works, then the claim is that we're observing a manifestation of a supersymmetry. And there is also another because it's a little bit late, I'm going to skip it. We can also make, there exists also some wild identity in the D dimension, which relates to the connected with the disconnected correlation function. And then there's also a way of computing it, but I'm going to skip that one. Let me just show you for one other quantity. So the disconnected correlation length, normalized as the dimension. And here I'm showing the numerical results where we compare with L minus omega. So we choose the omega of the 3-dimensional Ising model because we believe that it's the same, and we check it. So if I'm taking R, so R is the ratio of the elongation. If I'm taking R equal 1 and I'm extrapolating, I'm going to end up somewhere here. Okay. Next, I'm going to change R. This is R equal 2. This is R equal 3. R equal 5, and then we observe that for R larger than 5, basically it has converged. So it doesn't depend anymore on R. Okay, so R equal 5 or 10 is more or less enough for claiming that this is infinite. So then we're extrapolating this value, and boom, we're ending up with this result, which is the same as the one with the model. Okay, so this is one evidence that we're observing something which looks like this correlation of supersymmetry. We have the same thing for, I think I jumped, no? And we have something, the same for another quantity for the Binder cumulant here. So again, 1, 2, 3, and 5 or 10 as conversion. In that case, the Riemann is absolutely spectacular with the 3-dimensional algebra. Okay, and this is still for another one, but I'm going to skip it. And just to show in comparison, we made the same check in 4 dimensions. Comparing with the results in the 2-dimensional model, and in that case, it fails completely. I have to make consistently check. And I'm going to stop here after just summarizing my results. So what we have shown is that we have universality of a random Ising model in D dimension. We have some accurate results. We have shown that the whole set of critical exponents and that we have a 3 independent exponent. We have shown it in 4 dimensions. Our estimates for the critical exponent indicate that we have dimensional reduction in 5 dimensions, or at least we're very, very close to it. And then we also check this prediction with supersymmetry, and we show that this is well satisfied between the 5D random Ising model and the 3D Ising model. This is the procedure. Thank you.
Okay, thank you. That's a very thorough check and some nice results. So are there any questions?
Yes. Do you have an explanation why the dimensional reduction does not work between 4 and 2?
No, no, this was just measurements. We have just done measurements, and we're observing. It's like an experiment. We're observing, and no, but we don't have more explanation than
So should we think that somewhere between 5 dimensions and 4 dimensions, some other fixed point comes in, or some non-perturbative thing happens between 5 and 4 dimensions?
I don't know. Well, there is always works. The one already mentioned by Silvio, the work by Tarjut and collaborators, who claim that it's at 5.1 that we have something. And then there was the other works done by Sava and collaborators, who claim that it's 4.7 or something like that. And this next speaker is going to speak about, Emilio will speak after me on that. Maybe it's better if I let him speak about that. Okay.
You know what you actually have done. You have to remind you have a standard which allows you to.
Yes.
Marco, please make sure to repeat the question. We hear absolutely nothing here.
Oh, sorry. He asked us, Silvio was asking what we actually measured. And what we actually measured, we performed some large simulations. So this is the slide which I think I jumped over. So we have some programs using optimization method which computes the ground state. We are at 0 temperature, and we're using either a Gaussian or Poisson distribution. There is no degeneracy, so we just need to compute the ground state. When you have a ground state, it's like if you have a equilibrated system. So basically, you just need to compute the ground state of a model, and there exist algorithms in n dimension for a random Ising model working in the polynomial time. Okay, so we don't have a problem of equilibration, and then we are able to simulate a rather big systems indicated here. One key point of our simulations is that we have to run over for each run we have to average over 10 million samples to get enough statistics. Which takes a lot of time. Typically, the biggest system for each ground state takes 2 minutes. So I think if you're putting the total amount of time which is done on this thing, correct, 5 or 10 minutes, I think, depending on the computer and things like that. I think the total amount of time put into that one corresponds to, I don't know, 1,000 years of time on one computer, which of course we have not done on one computer, but more than one computer. Okay.
Can I ask a question?
Go ahead.
Thanks, Marco, for a very nice talk. So for the usual Ising model, not for the random field, in recent years, there is this systematic program by Martin Hasenbusch, who has the best Monte Carlo determinations of critical exponents for the Ising model and for other models, or 2 or 3 and so on. And so he's systematically taken advantage of finding improvements of the latest models, which allow him to kill the leading irrelevant correction. And then he is actually able to get extremely well, to nail down extremely well critical exponents of all these models, working at not so large lattices. So actually at pretty small lattices, but he gets best values, world record determinations in Monte Carlo. So I was wondering if using these tricks or any other tricks, you could get more convincing evidence if in 5D actually, the agreement between 5D and 3D, it would be better. I think we would benefit all from knowing, like.
Yeah, I'm afraid that if you're trying to improve your system, you're going to have less corrections, but then it's going to be difficult to find other algorithms which would work for the systems.
But in your system, there are 2 ways of improvement. You can improve your lattice action, like adding next to nearest, coupling to so, or you can play with improving the noise distribution. So are you sure that none of this could be used to improve your simulation chain?
Well, changing the Hamiltonian would be difficult because then if you're just putting a second neighborhood, there's going to be a I mean,
Okay.
here I said it's a polynomial time. The polynomial time depends on the number of neighborhoods. This is why we have 192 and 28. This is for having, there's a limitation due to the time, but in addition, there's a limitation due to the memory. If you're adding more and more neighborhoods, at some point, the program will slow. Okay. Just because you need too much memory. So adding a second neighborhood is going to be really difficult. Probably that is going to make things worse than anything. Checking for the distribution, yes, this has not been done yet. It's probably maybe there's a possibility of finding smarter distribution. I don't know.
No, but I mean, you were showing some curves approaching like from above and other curves approaching from below. So there's probably some curve which just approaches as a straight line in the middle.
Yeah.
There was this non-monotonic plot.
Yeah, I know that in the case in 3 dimension, which was first worked out by Fitas and Martin, Victor Martin Mayor, they have checked many of the distribution, they didn't find any. And
Okay.
I have another 2 questions. One, I vaguely remember that there were papers claiming that for the random field system, before you get into the ferromagnetic phase, there is an intermediate spin glass phase. I don't remember any details of that, but could that happen and then mess up your simulations?
no.
You
No.
can definitely show there is no such spin glass phase.
Yeah.
Okay. The other point I want to make is you are showing here 2 distributions. Both have a maximum at h equals 0, and they are decaying, moving away from there. If you had used a distribution which has a local minimum at 0 and 2 peaks at the 2 sides of h equals 0, like the distribution of plus minus h, then you would have a first order transition and a tricritical point. And then there could be all the intermediate distributions in which you change the shape of the distribution near h equals 0. How easy is it for you to play with that distribution?
It's possible. In principle, it works the same. The only thing is that when we looking the different curves and we're looking for intersections, sometimes we find some jumps, and then it's a little bit more difficult to deal with them. But in principle, it can be done. Yeah, it can be done. It's just more difficult.
I think it would be interesting because then you would test the dimensionality shift maybe of the tricritical point.
Yeah, yeah. No, it's in principle it's possible, but it's just more difficult. Yeah.
Are there other questions? Okay, so maybe it's time for a well-deserved break. So I'm sorry, I'm not quite sure. When do you want to resume actually? 4 o'clock?
Yeah, I think Emilio, who speaks later, has a problem of constraint of time because he has to leave at 4:45, so maybe not too late.
Okay, so let's make a 15-minute coffee break then. Until 15:45, and then we will resume.
Le fait qu'on arrive à